You know, on one of my favorite TV shows, Shark Tank, there's a gentleman named Kevin O'Leary who often says, I love cash flow. And in this business, we love redundancy. I haven't come up with a cool way to say it yet, but maybe you can and let me know about it because it's whether it's layer 2, whether it's layer 3, we love redundancy. A single point of failure for anything in today's networks really is not acceptable. We'll take all the redundancy we can get, we'll take all the backups we can get, but as you'd expect, and as you likely remember from your CCNA studies, redundancy works just a little bit differently at layer 2 as compared to layer 3. And just a quick reminder here, layer 3 routing protocols, EIGRP, OSPF, they allow us to use secondary paths in addition to the primary paths, which make equal and unequal cost load balancing possible. Now, some of that behavior is default behavior, as we know, and some of it's got to be configured, but it is there because with routing, we want to use as many of those paths as is feasible. Of course, that word rings a bell from EIGRP with your successor and your feasible successors. Now, at layer 2, our redundant paths, our backup paths, if you will, they need to be ready for action if that primary path fails. But by default, they're not going to be used in addition to that primary path. Because the basic purpose of STP, the spanning tree protocol, is to first identify valid loop-free paths, then choose the best of those paths for use, and to block ports on the valid but less desirable paths, holding those paths really in a kind of standby. Now, should a primary path become unavailable, STP is going to realize this and begin to unblock the necessary ports to put the next best path into action. Now, that's the kind of chock full of theory paragraph you look at and you go, okay, I got all that. What was the middle thing again? And we're going to see all of this in action. The first couple of videos, we're going to be doing some walkthroughs because there are some things about STP you really can't see on the switches. So we've got some walkthroughs, especially this next one where STP is not even operating. And then after that, believe me, we've got one lab after another. I've got some 2-switch labs for you, some 3-switch labs for you, some great labs that I've never included in a course before, and I know you'll enjoy them. But I do want to hit these walkthroughs first. There's some very important information here. Now, you say, what about those redundant paths, though? Say, okay, that's fine, but you're like me. If you see 3 paths from A to B and the data's only using 1 path, I'm already thinking, how can I use those other 2 paths? Why are they just sitting there? Why can't I use every single path from point A to point B for switching? Well, the problem at layer 2 is the possibility of switching loops. And the first thing I want to show you is a walkthrough of a situation where a spanning tree protocol is off. And just a quick note here, switching loops are sometimes called bridging loops. I will probably go back and forth between the 2 terms here just to get you used to that. This is true even in networks that don't have bridges, which is most of our networks. It's a legacy term, and why do we say legacy? Because we don't say old. Let's take a look at this network and see what would happen if STP did not exist. Now, this, my friends, is redundancy. We have hosts A and B sharing one Ethernet segment. We have host C and D sharing another one, but connecting those 2 segments, switches 1, 2, and 3. 4 hosts, 3 switches. That's a lot of redundancy. Just for reference, all upper ports here, the ones leading to hosts A and B on the switches, are fast Ethernet 0/1, and all the lower ports on the switches, the ones leading to hosts C and D, are fast Ethernet 0/2. Now, all we need is 1 frame to see things begin to go awry. And again, this is an example with the spanning tree protocol off. So let's say that host A sends a frame to host C. Well, we know that all switches then will receive that frame on their fast Ethernet 0/1 interfaces, the ones closest to host A. Now, those of you who got your CCNA with me, what's the first thing that the switch looks at on the frame? Because I say this about 300 times, it's very important. The source MAC address. Switch isn't worried about the destination MAC yet, it's worried about the source. And one of the reasons it does that, we'll bump into several in this course, but one of the reasons is, of course, that's how it builds its MAC address table. It's going to look at that source MAC address of the incoming frame and say, do I have an entry for this host? So the switches are each going to check the address table. We are assuming, by the way, an empty MAC table. Maybe the 3 switches just got turned on. And all three switches 1, 2, and 3 will say, hey, I don't have an entry for host A, whatever host A's MAC address is. I don't have an entry for that, so I'm going to make one that says that when I need to send something to host A, I send it out my fast Ethernet 0/1 port. So that's all fine and dandy. Then what's going to happen is the frame that's going from A to C, the switches won't have an entry for host C either. So what do we have? We have an unknown unicast frame, and that frame is treated just the same as a broadcast. It's going to be flooded. So switch 1, switch 2, switch 3 all flood that frame out onto their 0/2 ports. Just as quickly, we have a switching loop beginning to form, because each of the switches is going to see the frame that was just flooded on the 0/2 segment by the other two switches. And what is the source going to be? The source is still host A, because that source MAC address doesn't change. So each one of the three switches then says, oh man, I have an entry for host A, but I have an entry that says 0/1, but yet I'm getting a frame in on 0/2, so that means someone must have moved it. I will dynamically update that entry. So then, of course, that just keeps flapping back and forth, and as the four hosts start sending each other more and more traffic, you see more and more of that. Now, what we can end up with, too, that's bad enough, but if you think this is bad, wait till you go through a broadcast storm. Because as those frames keep getting flooded like that and the addresses keep changing from one port to another and more flooding occurs, you have the possibility of a broadcast storm. A broadcast storm does not happen all at one time. It is not a sudden event. I hate to compare it to this. It's kind of like a heart attack. A heart attack is a bad thing when it happens, but a lot of events led up to it. It just didn't suddenly happen. And what happens is, you might have a couple of people say, the network seems a little sluggish. Well, when do end users not think the network is a little slower, Do people ever think checkouts at the supermarket are, fast enough? So, you might turn a deaf ear to that. Okay, I'll check onto that. Just being human, and then you go do something else that you need to get done. So then, you notice the network slows a little bit. Maybe you're on the switch and you notice that as well. Well, it's the number of broadcasts the switch is having to handle going up and up and up slowly. And what happens is sooner or later they overwhelm the switch, and the switch is so busy trying to handle all these broadcasts and flooded frames that it can't do its job. So just that quickly and just this simply, we end up with a real problem. Switching loops basically cause three main problems. The first is that the frames can't reach their intended destination. Now, that could be totally or in part, but let's face it, both of those situations are bad. Secondly, you end up with an unnecessary strain on the CPU. That's always bad. And frankly, a lot of bandwidth gets sucked up. Not exactly a technical term, but you know what I mean, because more and more traffic gets flooded, it starts taking up more and more bandwidth, and each one of those situations, as far as the CPU load and the bandwidth load, each one of those just keeps getting a little worse and a little worse and a little worse until sooner or later, it gets very bad. It gets terminal. But thanks to the spanning tree protocol, we really don't have to worry about switching loops. We barely give them a thought today, frankly, unless we go in and start tuning up STP, which we're going to learn how to do, but you'll also learn it's not something you do a lot of. Now, preventing the switching loops and working with STP, it all begins with the bridge protocol data unit types, the BPDUs, and the root bridge election, and we will hit those at the very beginning of the next video.